So you don't see the document, right? Or do you? Uh, chat. I do. Good. Good. Thanks. Thanks for letting me know. Okay, so first again, my apologies for this unusual format of giving a tutorial. Now, so while giving the tutorial, I remind you that the chances are that if you write something, I may not notice. I will of course try to, but I may not. So if you want to ask something, please tell it. Okay, so by now I assume that you see the document I'm presenting, and now you see the white page where I will be solving that. Right, you see that I'm now writing tutorial sheet 2 because we are still on the second page, on the second exercise sheet. And so I assume you see everything and you hear me. That's also what I assume. If not, please let me know. So we good. So we're going to maybe we need to still do several basic exercises about efficiency in games, like finding all the mixed Nash equilibria and several solving a typical exercise where we need to exemplify certain properties of general games, and then we're going to move to the concrete games we will work with actually throughout the course. So by the way, before, well, I asked this in the end, is it fine if I share the recording of this tutorial for the for the benefit of those who have not been here? Is it fine with you? If not, I will not, but if possible, I would like to record and to share the tutorial. So you may think, and let me know if you don't want the sharing to be made, but your picture is not seen anyway. So, but anyway, if you participate, I respect your right not to be put on YouTube, on the YouTube channel, of course, if you don't want. So the following game, let's the first exercise, find all the mixed Nash equilibria. And that's probably the last exercise of this sort on the tutorial. We have a game between two players, player 1 and player 2. Player 1 has 3 strategies, 1, 2, 3 in Roman letters. Player 2 strategies are denoted with A, B, and C. And we need to find all the mixed Nash equilibria. As usual, the first step we do is deleting all the strictly dominated strategies, because we know that deleting those does not change the set of Nash equilibria. Of course, in the sense that we identify the equilibria when the deleted strategies were given 0 weight or 0 probability, with those where they just don't exist. In that sense, the equilibria of the game we get when we delete all the possibly all the strictly dominated strategies are the same. So, what are your suggestions? What can we delete, if anything? Which strategy? First player, her strategies, second player, or column player, her strategies. Which strategies can we delete? You write something? Okay, thanks. So if you have any suggestions, please let me know. I probably don't make it. But I apologize. I think if you have been speaking, I have not heard you because I've just turned on the. Okay. So I just turned on my sound. So no, actually that doesn't matter. That shouldn't matter. No, you have not been speaking. I see. Okay, sorry, that's the sound of another computer. Good. So uh, because I think I have to reconnect to enable. Okay. Well, nice. If you can, please do reconnect. Mhm.
Okay. You hear me?
Yes, I do. Oh, great.
Okay.
Now it's more convenient because now I don't need to constantly switch to that other window to see what you have written. Good. So do you have any suggestions what we can delete? I remind you that we talk about being strictly dominated. It can both mean that you are strictly dominated by a pure strategy or by a mixed strategy. But the dominated strategy itself we talk about is pure.
Yes. Strategy A dominates strategy B.
A dominates B, correct. So we can already delete B. So actually, let me maybe write it like that. Problem 2, because problem 1 I solved at the previous tutorial. So B is strictly dominated by A. So if I quickly write this matrix, I assume that you see everything, including what I'm writing, not only yet because I basically share the whole screen, but so okay. It was 151341. 1430235. 222113. Great. So first B is out. And now what can we say? So A and C, no domination among them, right? Because 5 is greater than 1, but 3 is smaller than 5. Can we rule out anything from the row strategies?
Yeah, strategy 2 dominates strategy 3.
2 dominates 3. Correct. Now that we've deleted B, because before it was not the case, of course, but now it is. So 2 dominates strategy 3. Great. Now 3, I write it 3 is dominated because that's what matters. 3 Romanov. Yeah, that's his name. 3 is dominated by 2, and now 1 is smaller than 4. Okay, I hope you see my mouse, so I point at that. 1 is smaller than 4, 4 is greater than 3, 5 is greater than 1, but 3 is smaller than 4. Okay, now we don't have anything. So now the process of iterated deletion of strictly dominated strategies has terminated, and now let's actually look for the equilibrium, which we know are exactly the same as in the original game. Simply the deleted strategies have 0 weight in all the equilibria in the original game. So what are the pure equilibria? What is the set of the pure equilibria? Yes.
I don't think there are any pure ones.
Let's see. 1A is not because player 1 would like to deviate to strategy 2. Actually, we can redraw game, with only the remaining strategies may be more convenient. 1, 2, and here you have A and C. 1, 5, 4, 3. Great. So 1 A is not because 1 would like to deviate to 2. 2A is not because player 2 would like to deviate. 2C is not because player 1 would like to deviate, and A1C is not because player 2. Kind of matching pennies only with other number. Good. So no pure equilibria. Are there any partially mixed equilibria? Actually, I think that you took the general game theory course, right? So for you, it's well known.
Yes.
With you, we can do it much quicker because you are the one who are here. The others will watch it hopefully online, but your benefit is more important because you are here. So let's do it quicker. Partially mixed. Are there any partially mixed?
I don't think so. But I don't quite remember the definition. I have to look that up.
Good. So I'll tell you. So the partially mixed. They basically ask me here when you have any question, because that's why we have tutorials to indeed basically kind of to practice the definitions to make them more memorable. So partial mix means when one of the players, generally one or more, play a pure strategy, whereas some other players, the other players play mixed, strictly mixed strategies. Every pure can be called mixed, but I mean when they actually mix among at least two strategies. So can it be that player 1, for example, plays a pure strategy, but player 2 mixes? And here indeed it cannot be, because in order to mix while best responding, both pure strategies or more among which you mix need to be optimum, because otherwise it will not be a best response. Here you cannot mix, or you cannot mix in an equilibrium, because if player 1 plays strategy Roman 1, then the only optimum response, pure response of player 2 is A. And she can never mix because C is suboptimal. And the same goes with all the other cases. If player 1 plays strategy Roman 2, the only optimum best response of player 2 would be C. 5 is greater than 3. And the same with the other player. If player 2, the column player, plays A, then the only optimum best response of player 1 is 2, because 4 is greater than 1. And if player 2 plays C, the only best response is 1. So no partially mixed, because every pure has exactly one best response. One pure best response. There is therefore no best response can actually really mix as one pure best response. Okay, let's just find the similar logic we employ when we look at the fully mixed equilibrium, when all the players mix among at least two strategies each. Yeah, there are only two strategies left. And here I guess you remember that we just denote the probabilities of each strategy by P and Q.
Yes.
Clean stuff. And then, and the condition, by the way, that's similar to what we just said. So P and 1 minus P, the probabilities of 1 and 2, and the probabilities of A and C, Q and 1 minus Q. And then the condition is that you need to have at least two strategies, your strategies which are optimal. Then you are allowed to mix it in the best response. So, for example, here you have again. Here it's quite a simple case because we have only two strategies, which are pure strategies for each player. So the condition on the P probabilities, on the probabilities of the first player, is that the second player has the same expected utility from both your pure strategies, A and C. That's a necessary condition for the second player to be able to actually mix between those strategies. It does not force her to mix, but she may mix. And the symmetric condition will be on the Q. So the condition on P is that what player Q gets when playing A, which is expected 5P plus 3 times 1 minus P, is equal to what she expects when playing C, which is 1Q plus 5 times 1 minus Q. Agree?
Should it be 5P plus 3, 1 minus P?
Yes.
Equals to 1P plus instead of Q.
Right. I'm thinking, okay, you're right completely. My bad.
But otherwise, the numbers are correct, I think.
Sorry, my apologies. I definitely consider it's not the right way. P, you're right, thank you. And the same with Q. So the expected utility of player 1 when playing your strategy Roman 1 has to be equal to her expected utility when playing your strategy Roman 2. So what is her expected utility when playing Roman 1? Maybe you want to tell?
1 times Q plus 4 times 1 minus Q.
1 times Q plus 4 1 minus 4, right?
Equals 4Q plus 3 times 1 minus Q.
Equals to 4 times Q plus 3 times 1. Correct. Those are the conditions, and they are necessary for someone to be able to mix. They don't force you to mix. What forces the player to player 1's P has to be chosen such that player 2 has the equal expected utility. That's what can force you to mix. But not she doesn't have to mix in general if her strategies are both optimal. So player 1's strategy is adjusted such that the second player, the other player, has both strategies give equal expected utility. Okay, so we don't even have to solve it, but maybe let me really quick maybe do this. It doesn't really.
I can also just tell what I calculated.
Okay.
So for P I had 1/3, and for Q 1/4.
I don't remember what's the answer. Let me just open the solutions, then I tell you. Yes, correct. And these are the only equilibrium. That's also what I have. And these are the only, so the set of mixedness equilibria is 1/3, 1 minus 1/3, in other words 2/3, and 0 for the strategy we have deleted. And the second player is 1/4, then 0 for the strategy we have deleted, and then 1 minus 1/4, in other words 3/4. Good. Oh, yes, that's the, well, I of course need to write it properly. That's the set of mixed fields. There is only one mixed field. In particular, it means that, by the way, the products of strategy and stability are both equal 1. Or to 1. Sorry, not to 1. They're both equal because there is only one mixed field. To what they're equal, we need to look at the optimum social welfare and then to compare them. I remind you that the optimum social welfare can be looked at just in pure strategies, but that's not a question. This question. Let's move to the second question of this tutorial sheet, and that's a simple, or not so simple sometimes, question about efficiency example. So, as I like, we need just to either provide an example of a game with such properties, or to prove that no game can have such properties. And as I write, the default social welfare is the utilitarian one. It means that it's defined as the sum of the utilities of the player. So what about the first example? If there is such a game, can you give me an example of such a game? Price of anarchy is 2 and price of stability is 1. Let me write here. So problem 3.1. So price of stability is 1. Means that there is an optimum equilibrium. Price of anarchy is 2 means that the worst equilibrium, however, is twice worse in the social welfare. So if you have any suggestions, let me know, please. Just checking.
Yeah. I'm trying to think of something.
We can think of a game first. Well, you have 2 equilibria, or maybe more, but let's think the 2 are enough, which have different social welfare. Can you just think of a game? One is good, the other one is less.
We could choose a game with 2 strategy sets just as 0-0, and then the other 2 as, for example, 1-1 and 1-1/2. So those 2 would be the Nash equilibria, and then we should have price of anarchy 2 and price of stability 1.
So 2 players, right? Let's try the simple. Okay. Let's call the strategies top, bottom, left. So can you? So here you want 0-0, right?
Yeah, 0-0 or doesn't matter.
In top right, what do you have?
1-1, for example.
Budget the R 1-1.
Then the bottom left 1-1/2.
And then
0-0 for the last.
Okay. So here you have two equilibria, bottom left and top right. And correct, the social welfare optimum is 2, and it's attained by TR. And the bottom L has a social welfare of 1. I mean, half plus half. Half, that's twice 4. Exactly. Yes. What about the second? Can we have such a game?
No, that's impossible because the minimum social welfare cannot be larger than the maximum.
Correct. By definition. Press anarchy is the maximum social welfare overall. I'm writing it informally, as actually I can write it formally. Divided by the minimum social welfare in an equilibrium, let's say whatever, T. And that at least what you have the same nominator but a different denominator, which is actually greater. Maximum, which is the definition of the price of stability. Correct. Let's move on. What's on the next question? So assume that the price of stability is infinity. No, I misread the question. Give me a game where the price of stability is infinity, or prove such, because there are such games. And then the question is, what about the price of anarchy of thought? So give me a game first where the best equilibrium is already infinitely bad. Actually, before that, we already can tell that, of course, the price of anarchy is also at least infinity, namely, it also has to be infinity. If the best equilibrium is infinitely bad, definitely the worst one will be. And then the question is, what are such equilibria? Can you give me some example? Or you can also adjust the example you've given me. No, it's actually hard. So forget it. It's not exactly.
I think Prisoner's Dilemma with adjusted values could work for that.
Yeah. Actually, I think you are right. Let's try. Yes. Adjusted. So we want the equilibrium to be bad, infinitely bad. Let's make it 0, 0. Relative to the best social welfare, which is something positive. Let's say 3, 3. And then to make it Prisoner's Dilemma. Right? Yes. Make it Prisoner's Dilemma. We need just to adjust if I made. If the other person defects and I suddenly cooperate, I don't like it. That's -1. But being the only defect gives me 5. I think now it's 5. Because now DD is the only Nash equilibrium. It's also the excuse me, dominant strategist equilibrium. So 0 is strictly larger than -1, and 5 is greater than 3. And here indeed the price of stability even, which is actually even the price of equal to the price of anarchy, because there is only one equilibrium. Excuse me. Is equal to 3 plus 3, the optimum, social optimum, plus 0 divided by 0 plus 0, so it's of course plus infinity. I really don't like the games. We need to drink something. Well, with negative values, because then the price of anarchy and stability, the definitions start getting kind of airy, but I think it's kind of fine when we make it here. We still don't define on negative by negative numbers. Don't define. We don't have negative numbers in this expression. Anyway, that's a correct example. And let's move on. Can you have a game? Well, so when I was defining the price of stability anarchy, I said that if the fraction happens to be 0 divided by 0, then I just take it to be 1, because that means that still it's optimal. But now the question is, can you give me a game where this is actually 0 divided by 0?
Yeah, a simple game would be just 2 players with 2 strategies, and every strategy set is just 2 zeros.
Correct. Yes. For example, the identical, the constant 0 infinity, or in other words, it doesn't have to be 2 players, but in the case of 2 players, it's going to be just a matrix of 2. Great. Let's move on. So the fifth question is actually a bit lengthy, but actually it's actually cool. A game where using the egalitarian social welfare, which I'll now remind, would change nothing in the definition, in the value of this game of the price of anarchy. So when I just look at the game and I use this, so I use so a reminder, the utilitarian, the default utilitarian social welfare is the sum of the utilities of all the players in this strategy profile. It's always in a given strategy profile. Now the egalitarian is just the minimum utility, and you want to optimize the worth of play. Just the minimum utility, the worth of play in this profile. And the question is, given those definitions of social welfare, I would like to have a game, or prove it's impossible, where moving from the definition of the social welfare in the utilitarian sense, namely as a sum, to the definition as the minimum utility, nothing would change. Nothing, I mean, neither price of anarchy nor the price of stability would eventually change. Then this question contains several questions. First, nothing. Then just the price of anarchy would not change, but the price of stability would. Then the price of stability would not change. And of course, I should have written that way. Because you can say that, okay, when nothing changes, also the price of anarchy in particular doesn't change. I mean that nothing. I mean here that here nothing changes. So both price of anarchy and stability remain the same, and moving from one definition of partial warfare to the other one, then the price of anarchy remains the same, but the price of stability changes, then the price of stability remains the same, the price of anarchy changes, and then both price of anarchy and stability change. So let's start with an example where nothing changes. I want, in other words, nothing is maybe two sweeping statements when neither price of anarchy nor the price of stability change. Let's look at that example.
I think a simple example would be the same game as before, so with a constant 0.
Correct. Always actually any other constant number. Because the ratios wouldn't change when you take a minimum or you take the sum. The ratios would change. Or utility 0 or any other constant. Let's now look at the second question. A game where only the price of anarchy doesn't change, but the price of stability changes. So do you have any suggestions? Only the price of anarchy doesn't change.
I can't think of anything right now, but I have the notes from the game theory lecture here.
Okay, great. Maybe use some example from the lecture.
I had a game there with top left 1-1.
Yes.
Then top right -1/-1. Bottom left also -1/-1. And 1-0. So we have two equilibria in the top left and bottom right.
Right.
And the maximum social welfare, the utilitarian one, is 2.
Right. Let's actually do. Let's look. The price of anarchy here is the optimum, which is 2, 1 plus 1, divided by the worst equilibrium, which is 1 plus 0, right? With the utilitarian. Utilitarian 2 divided by 1, 2. And the price of stability, the utilitarian, is 1 plus 1 divided by 1 plus 1, so it's 1. Now the egalitarian values will be egalitarian the person of anarchy will be now if we take the minima, the optimum social welfare, what is that in the minimum when we take the minimum? What is the optimum social welfare here? 1, right? Do you agree that it's 1?
Not sure.
So let's look at it. So what is the social welfare in the egalitarian? The minimum among both players. For example, when one player gets 1 and the other player gets 1 as well, it is 1. When one player gets -1 and the other gets -1, it's -1.
Yeah, so here it's 0.
So when one player gets 1, the other one gets 0, it's 0. Now, what is the best minimum? It's the maximum or the minimum? Maybe a bit confusion. So when we look at the sum as the social welfare, we ask what is the best social welfare, and it was about what is the largest sum. Here, when we look at the minimum, we ask what is the largest minimum.
Yeah, 0.
No, because
from the equilibria it's 0 and from all strategies it's 1.
Yes. So when we look at the all strategies is 1, because 1 yields us a minimum of 1. Now from the equilibrium, now we look at the equilibrium, the worst equilibrium. So the equilibrium 1, minimum is 1, and the equilibrium 1, 0 is minimum is 0. So the worst equilibrium is 0. Do you agree now? Shall I repeat if you don't understand something?
No, that's what I have noted here as well.
Good. So that's infinity. The price of anarchy has changed, and that's not an example for what we need. But let's continue. Maybe it will be an example of something else. The price of stability is 1 divided by the best social. Yes.
Yeah, I also mixed this up. Yeah, this was an example for only the price of anarchy changes, so I mixed it up.
Okay, but we'll use it later.
Yeah.
Now, the price of stability is 1 divided by the best social welfare in the maximum minimum, which is also 1, so that's 1. So that's an example where only the price of stability remains the same. That's another example. Let's look at the example where only the price of anarchy remains the same. We actually may change the question here and tell that was for the price of stability remaining the same. Now let's look at for another example where only the price of anarchy remains the same. Because the price of stability is here also the profile with the maximum social welfare, we simply give both players the same value. I mean this profile 1, and then it works. The ratio doesn't change whether you take the sum or the median. But what about the price of anarchy? What is the problem? The hard question is that if we have the best equilibrium also give us the maximum, the optimum social welfare, then the price of stability will always often not change. Actually doesn't have to be. Actually, it actually is fine. Let's look at the example. Let's continue. Continue. I'm trying to find how to zoom it out. It doesn't matter actually. Doesn't matter. Let's just continue. So, do you have any suggestions? First of all, let's try to change the price of stability. We want the price of stability to change. We can take a similar example, but I don't like the negative numbers, so we can, why not? So 1, 1, make it 1, 2. And then it's going to be the best equilibrium and the maximum Koshava. Then the ratio will change from 1 plus 2 divided by 1 plus 2, which is 1, to... No, it will not change, because then we need, if we want the price stability to change, we need the optimum to be not an equilibrium, because otherwise they just change together. They will be just always one. We need the optimum to be not the equilibrium. For example, 3, 4. Here it's going to be the optimum 3, 4. That denotes the top bottom. We start with top bottom, left right. But we don't want the top right to be an equilibrium. We want it only to be the optimum. So it won't be the equilibrium because there is a way to get 3.1. Not 3 times 1, but 3.1. Three. I think. Okay. Let's see whether we have what we need. But we want the price of stability not to change. So sorry, we want the price of anarchy to remain the same. Think like that. One second. Okay. So here, so what are the equilibria?
Just the bottom right.
Right, but I want also the top left to be the equilibrium. So let's change it to No, I don't want. Second place. Second place.
I believe I have an example from the other lecture.
Great. Give me your example.
So top left was 2-1.
2-1, yes.
Then top right 1-1.
Yes.
Then 0-0 in the bottom left.
Yes.
And 1-0.
Okay, so let's see. Who is the equilibrium? What are the equilibria here?
Top left and bottom right.
Top left. Top right is also an equilibrium.
Yes. Yeah.
Maybe it's fine, but let's see. And then it's also bottom right. Yeah.
No, I don't think it works. I thought this, no. Because then the minimum egalitarian welfare is over the equilibrium is... Oh no, still 0.
Let's see. Usually, so you say it doesn't work, yes?
I'm not sure. I thought it worked.
Well, let's see. Utilitarian. So the price of anarchy is what?
The maximum social welfare is 3. So 3 divided by...
the worth 1 plus 0. 3. And the price of stability is what? Also 3 divided by 3, 1. And let's look at the egalitarian case. The price of anarchy is 1, because the minimum is at most 1.
No, it doesn't work.
No.
No.
By 0, the price of anarchy doesn't, yeah. And yeah, okay, it doesn't. Okay.
I somehow had a 0 in infinity for the top one as well, but that was wrong.
Let's look for another. You know what? Let's make a 10-minute break and then look for another example after the break. Like till 5 past. Okay?
Okay.
We'll see you in 10. So for those who are watching it recorded, I forgot to place unpause recording, and now we've already solved, finished the exercise 3, efficiency example, and probably I'll publish the solution. So good. I'm glad we are quite efficient today also. And now let's go to the next next tutorial sheet, and that's number 3. So here we are getting actually to the games we are going to work with throughout this course. Slowly, but we are getting there. So remember the famous Pigo example. Now I want to solve the Pigo example with unbounded. Well, let's go to the book. It's basically an example from the book. Most of this course follows. No. So we need to go page 459 in the book, 17.1. 500, 400. Okay. This book is freely downloadable online, by the way. I think that you have already downloaded it. It's not. I can send it to everyone because that's freely downloadable. The version I'm using is downloadable. Good. 17.1. So remember we had this famous Pigo example. Plus we can just also open this in the book. Uh, 17. 17.1. Okay. It's not open on slides, but rather on the book, because to understand the question, we will better see how the book denotes stuff. Maybe they have a different notation. I think that the resource allocation game, they had a bit of a different notation. Nothing different, nothing substantial, simply a different notation. So the Pigo example was that there was two edges between source and sink, and the source and destination, and you need to route one unit of flow. And the upper edge had this constant cost of 1. The lower edge had the cost which is equal to the amount of flow routed through this edge. Well, that was the Pigo example. Now, imagine that the lower edge has the cost which is not just cost of x to z, but rather x to some power, this one, some power d. What's the price penalty then of the resulting network? So is the question itself clear?
Yes.
Okay. Let's solve it. I think the further we go, the more instant stuff becomes. Because now we actually are going to solve more practical related, less, sometimes more, sometimes less technical. So okay. So tutorial sheet 3, right? It's already 3. Exercise sheet 3. Problem 1 means that exercise 17. Point 1 from page 459 in AGT. Okay, now we are going to solve that. So imagine that the network is like that. The upper edge has the cost of 1, regardless what flows. Yeah? And the lower edge has the cost of x to the power of d. And the question is, what's the price of 1? So we need to find what happens to the best flow, and what is the best optimum social optimum flow, and what is the flow which is the equilibrium flow, some equilibrium flow with the RSF. So what is the equilibrium flow?
I believe it's when everything is on the lower edge, so on the yeah.
Right, because the total amount of flow the flow is 1. I think the tails will say it here, right? Do they say that? Okay, let's go. So, please repeat what you just said.
So basically, all the weight is on the lower edge.
Right, because if something goes through upper edge, the lower edge becomes strictly more profitable. So for any x which is smaller than 1, x to the power of d is strictly smaller than 1. And so the cost of the lower edge is strictly smaller than the cost of the upper edge. And therefore, the unique equilibrium flow is to channel everything through the lower edge. And its cost is what?
1, I think.
1 times the cost it incurs, which is 1 to the power of d, exactly 1. Right. Now, what is the optimum flow? So let's denote the flow through the lower edge. Now, the next denote the flow through the lower edge by t, x, right? Denote by x, and then for the upper edge, what remains for the upper edge? 1 minus x. The upper edge costs 1 minus x. And what does it cost? Denote this by just x, because it can be described by one variable. So the cost of x is equal to the, so the lower edge costs x times the x to the power of d, plus the upper edge costs 1 minus x times 1, because the upper edge costs 1 every time. Do you agree?
Yes.
Great. Let's then continue. One second, I have focused the mouse. Now we just optimize. This expression is x to the power of d plus 1 minus x plus 1. The first derivative is just d plus 1 times x to the power of d minus 1. That's the first derivative. And that's equal to 0 if and only if x is equal to 1 divided by d plus 1, and that's to the power of 1 over d. In other words, the d not square, but the d root. You can also write it, but that's math actually. It won't matter. Let's not waste time. Oh, is that indeed an extremum? And if yes, is that a minimum? Because we want to minimize the cost. Let's look at the second derivative, and that d plus 1 times d times x to the power of d minus 1, and that at any, in particular when x is equal to this value we have found, that is strictly greater than 0. And that's why that is, the second derivative is positive, strictly positive. That's a local minimum. And since there is only one local minimum, so it's also the global minimum. Continuous function. So that's exactly what we found. So that's the only global minimum. That's what we need. And that we just need to compare the social welfare, the cost. Sorry, that's analog. That's the analog of social welfare in the case of flows, but that's formally called the cost of flows. So its cost is equal to what? Again, it's simply substitution. You just substitute that value to the expression we have found. So the expression for the cost is this expression, and the value we have found is this value. We've proven it's the value we need, the only value which minimizes the cost, and its cost is equal to, substitute that to this expression. So basically, it's going to be that to the power of d plus 1 minus that plus 1, and then the price of anarchy is actually the worst cost in an equilibrium flow divided by the best possible cost. What is the worst cost in the equilibrium flow? We already found it's 1. And so the price of anarchy is actually 1 divided by this expression. I don't even want to copy it to avoid wasting time. Do you agree?
Yes.
Great. So I think that we are done with the exercise. We can try to make this function look a bit more civilized and then work with it, but let's not do it now. If we need it someday, we'll do it. Let's go on. Now actually, yes, I'm listening.
I just wanted to say that I wanted to leave now, don't have
okay,
multiplier.
sure. Okay, well, then since you are the only person which listens online, then let's just finish the tutorial and then next time we continue. Great. So I've published the first homework. It was kind of basic, and see you next. Hopefully, already. Hope you can manage it, and I hope I can too. So then, see you next week.
Yeah.
So you don't mind if I publish this recording for the sake of the benefit of the other students, right?
Yes, it's fine.
Great. Bye. Thanks.
Yep, bye.